in this part of the review, this is the second part, part 2. We'll try to complete this one and cover maybe this one, and if we have time to go into phrase 2. This is, as I said in part 1, this is the information retrieval course. We are reviewing the material of chapter 1 and chapter 2, and we are basing all the lectures and the slides on this book, which is Introduction to Information Retrieval by Christopher Manning and others. And this is the formal website of the book. Last time we were talking about the algorithm that does an intersection between two posting lists in an inverted index, which is this algorithm. And we concluded last time by showing this animation that demonstrates how the algorithm works. Indices, two posting lists. The other one is for Caesar. 1, 2, 3. To show in a kind of slow motion how the algorithm works. We have 2 pointers, pointer 1 and pointer 2. And pointer 2. So what happens is that once the 2 pointers are pointing to 2 different documents, we compare the 2 documents. If they are like this one, if they are not equal, we advance one of them. We advance the one with the list, with the smaller document ID. So pointer P2 is pointing to document ID 1, and pointer P1 is pointing to document ID 2. So this is smaller. So what we do is we advance P1, P2. We advance P2 instead of here. P2 will point to document 2. Now P1 and P2 are pointing to the same document ID, so the answer 2 is one of the documents. Document ID 2 is one of the documents in the answer set. This is the answer set. So now the 2 are equal. If the 2 are equal, we advance both pointers. Pointer 1 is moved one step forward, and pointer P2 is moved to the next document, which is document ID 3. We compare the 2. This is smaller. So what we do is we advance P2 to the next one. We compare them. P1 is pointing to 4, P2 is pointing to 5. This is smaller, so we advance this one. P1 is pointing to 8. P2 is pointing to 5. So which one do we advance? P2. P2 goes to 8. So we compare. Are they equal? Yes. P1 and P2 are pointing to the same document ID. So 8 comes here in the answer set. So now since they are equal, we advance both. We advance both pointers. We compare 13 is smaller than 16, we advance P2. Now this is smaller, we advance P1, and the idea is very clear now. So how this is how the algorithm works. So let's run the animation one more time and just try to have this, keep this idea in mind and see how it works there. 2 and 2 is our matching. We go back to the answer set. We advance 2 to 3. Okay, and it's going so fast. Okay, now 8 and 8 are matching. We advance both. 13 is smaller, we move it forward. 16 is smaller, we move it forward. And then basically it ends when we go to the end of the list. So this is the merge algorithm, and the performance of this algorithm is big O of x plus y. X is the length of the first list, and y is the length of the second list. So we can see that this is linear. Big O of x and y, not x squared or y squared, so it is linear. So it is really considered what? Is it good or not good? It's fast, it's good. And this is the pseudocode for the algorithm. So this is this portion, the inverted index, and how we do query processing when we have an inverted index. Now, there is an improvement to the inverted index by adding skip pointers, and that will be in chapter 2. So we need to go to chapter 2 of the book, or the slides, and now this is an inverted index with skip pointers, not only next pointers, but we have, in addition to the next pointers are these. These are next. So this is a skip pointer, and similarly for the first list we have skip pointers. This is mainly to speed up the processing of the query. We add those skip pointers. Now, to see how they work, we have this example that shows us how this one works. What we do is, initially we have 2 pointers like there, pointer here and a pointer here. Instead of moving to the next, what we do is we look at the skip pointer to see what is the end value of the skip pointer. The skip pointer is pointing to document ID 11. So we look at that. We examine this number before we move along the next point. So what we do now, we have skip is pointing to 11, and we have there 2. 11 is larger than 2. Pointer 2 is here, pointer 1 is here. Now pointer 1 skip is 11. 11 is larger than 2. So what we do now, because 11 is larger than 2, we come back to the next, and we just follow what we did there. We move next until we find a match. We have a match here. 2 goes back to the answer set, and then we proceed normally. Now we hit a node in the list with a skip pointer there. So now the pointer 1 and pointer 2 are pointing to 11 and 41. So we look at 11 because it is the smaller value. 11 is smaller than 41. So we need to move the pointer forward. So do we move it along the next or along the skip pointer? So what we do is we examine, just like we did here, we examine the end of the skip pointer. It is 31. 31 is smaller than 41. So now we are guaranteed that there is nothing in between this one and this one, nothing here that matches 41. So why? There's no need to go next. So we save the next steps, and we go directly, follow directly the skip pointer, and come here and start compare. So that's how we save time. We save the comparison between this and this and this and this, and we save the next operations. So this is the idea of an inverted index with skip pointers. Now the question is, where do we put the skip pointers? How many nodes do we skip? 2 or 5 or 7 or so that there is a heuristic which is basically, we'll come back to this in a minute. There is a heuristic that says that we do square root of L, where L is the length of the posting list. So if we have a posting list of, for example, here I think it is 16. How many are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So square root of 11 we truncate or we approximate to the next higher number if it is a fraction. So if we have a list of 16 nodes, we skip 4. If we have a list of 100 nodes in the posting list, we skip 10. If we have, let's say, 10,000, we skip 100. So this is the number of nodes we skip. We use a heuristic which is square root of L, where L is the number of nodes in the list, in the posting list. We conclude this part by this animation. This shows 2 lists. This is a list of posting list of document IDs. And this is another list that has only 1 node. So we want to show how the idea of skip pointers work by following this animation step by step. So we have 14 and we have 2. Okay, now we are starting. 14, it compares 14 and 2. 14 is higher. So it follows, it looks at the end of the skip pointer here. What do we have at the end? We have 10. 10 is smaller than 14. So it jumps over the skip pointer and goes to 10. So now we have 10, we compare 10 and 14. 10 is smaller still. So what it needs to do, it looks at the end of the skip pointer, it finds this 15 is larger than 14. So now it has to go back and follow the next until it tries to find a match. So it follows one by one, next, until 14 and 14 are found to be matching. And so that is the answer. Document 14 contains the answer to the query. Okay, this is the end of part 2. Thanks.